Hello there, and welcome to the Sleeping Physicist. If you're someone who likes to unwind by thinking about stars, particles, and the quiet structure beneath reality, you're in the right place. Tonight, we'll let our attention drift gently into real physics and real discoveries. Some of what you'll hear may sound surprising, but all of it is grounded in what physicists actually know. And if you enjoy these slow journeys through the universe, you're welcome to like and subscribe. But for now, get comfortable. Let your body rest. Let your thoughts wander. And let's begin. What is Planck energy made of, according to quantum physics? Long before anyone spoke about Planck energy, physicists were facing a quiet but persistent problem. The laws that describe the universe worked beautifully in their own domains, but they did not agree with each other at the deepest level. Gravity described the motion of planets and stars with smooth certainty, while quantum physics described atoms and particles with jittery precision. Each theory was successful, but only within its own scale. When physicists tried to imagine situations where both gravity and quantum effects mattered at the same time, the mathematics began to lose its footing. Predictions stopped making sense. Quantities became infinite when nothing physical should be infinite. At the turn of the 20th century, Max Planck noticed something subtle but profound. Certain constants kept appearing in nature, no matter which physical system was studied. The speed of light, the strength of gravity, and the smallest unit of action in quantum physics were not arbitrary numbers. They seemed woven into the structure of reality itself. Planck realized that by combining these constants, one could define natural units of length, time, mass, and energy that did not depend on human choices like meters or seconds. These units would belong to the universe, not to us. Planck energy emerged from this idea as a kind of reference point. It was not introduced to describe something anyone had measured, but to mark a boundary where our existing theories could no longer be trusted to operate independently. Just as a map becomes unreliable at the edge of unexplored terrain, physics needed a signpost indicating where familiar rules might dissolve into something deeper. Planck units were created to place that signpost, using the most fundamental features of nature itself. To understand why this matters, imagine measuring the ocean using ripples on the surface. As long as the water is calm, those ripples tell you something real. But during a storm, the ripples are no longer separate from the waves beneath them. At extreme scales of energy, space and time themselves may behave less like a calm surface and more like a stormy sea. Planck energy marks the point where the ripples of quantum physics and the waves of gravity can no longer be separated. This is why physicists did not ask what Planck energy is made of at first. They asked why their descriptions of reality stopped working. Planck energy arose as a response to that failure, a quiet admission that beyond a certain scale, energy, space, time, and gravity must be understood together, or not at all. Energy, before quantum physics reshaped it, was understood as a smooth and continuous quantity. It was something objects could possess in any amount, increasing or decreasing without restriction. A moving stone had kinetic energy because it was in motion. A lifted weight had potential energy because gravity could pull it downward. Heat was energy spread through the microscopic motion of particles, and light was energy carried by waves moving through space. In every case, energy behaved like a fluid that could be poured, divided, or transferred in endlessly fine portions. This classical view treated energy as a bookkeeping tool, a way to track how motion, heat, and forces changed form while preserving an overall balance. If energy disappeared from one place, it had to reappear somewhere else. Nothing about this picture suggested limits on how small or large energy could be. In principle, you could imagine a vibration with half the energy of another, or a thousandth, or a millionth, without encountering anything strange. This understanding worked extraordinarily well for everyday phenomena. Bridges stayed standing, engines ran, planets followed their paths, and stars burned steadily. Energy conservation became one of the most trusted principles in physics because it held across such a wide range of experiences. But there was a quiet assumption built into this success, that energy could always be subdivided smoothly, like slicing a loaf of bread thinner and thinner without ever reaching a final slice. As experiments became more precise, especially those involving light and heat, this assumption began to crack. Certain systems refused to exchange energy continuously. They behaved as if energy could only be absorbed or released in specific amounts, skipping over the values in between. Classical physics had no place for this behavior. According to its rules, energy should slide, not jump. Before quantum theory arrived, this posed a deep puzzle. Energy itself did not seem to be failing. The idea of energy conservation still held firm. What failed was the assumption about how energy could be distributed. Something about nature imposed a structure on energy that classical physics had never anticipated. Understanding that structure would eventually lead to Planck's insight, and with it, a radically new way of thinking about what energy really is. As physicists struggled with these stubborn experimental results, one problem stood out with unusual clarity. When objects glow from heat, they emit light with a specific distribution of colors. Classical physics predicted that hotter objects should pour out enormous amounts of high-energy light, far more than was ever observed. This disagreement was not subtle. It was catastrophic. According to existing theory, even a warm object should radiate infinite energy at short wavelengths, which clearly did not happen in reality. Max Planck approached this problem with caution rather than rebellion. He was not trying to overthrow classical physics. He was trying to make the equations match what experiments were showing. In doing so, he made a mathematical adjustment that seemed almost trivial at first. He assumed that energy could only be exchanged between matter and light in small, discrete packets, rather than in a continuous flow. These packets were proportional to the frequency of the light involved. At first, Planck treated this as a formal trick, a convenient way to make the numbers work. But the universe responded as if it recognized the rule. The equations suddenly aligned with observation perfectly. The glow of heated objects made sense again. Energy was conserved, but it was no longer smooth, it came in steps. This was the first time energy revealed a grain-like structure. Not grains in space, but in action, in exchange, in how systems changed. Energy was still not a substance, but it was no longer infinitely divisible. Nature appeared to have a smallest unit of energetic action, and everything else was built as multiples of it. This insight quietly transformed physics. If energy itself was quantized, then motion, vibration, and radiation were not as continuous as they seemed. They were underpinned by an invisible discreteness that only became apparent under careful measurement. The calm surface of classical physics concealed a deeper texture beneath. Planck did not yet know what this meant for space, time, or matter itself. But by discovering that energy came in discrete amounts, he unknowingly laid the foundation for every quantum idea that followed, including the strange scale where energy becomes so concentrated that it reshapes the very fabric of reality. Once energy was understood to come in discrete exchanges, physicists began to notice something even more intriguing. Certain numbers kept appearing whenever the deepest laws of nature were written down. The speed of light set an ultimate limit on how fast information and energy could move. The gravitational constant determined how strongly mass and energy shaped space. Planck's constant fixed the smallest scale at which quantum effects could occur. These constants did not describe particular objects, they described the universe itself. By combining these constants, physicists found they could construct a natural scale of energy that did not belong to any specific particle, force, or process. This energy emerged purely from the structure of the laws that govern reality. It was not chosen, it was unavoidable. When the constants were woven together in the only way that made dimensional sense, Planck energy appeared automatically, as if the universe were quietly revealing a built-in reference point. This construction is important because it tells us what Planck energy is not. It is not derived from chemistry, nuclear reactions, or electromagnetic radiation. It is not tied to temperature, motion, or vibration in the usual way. Instead, it is assembled from the limits of how fast anything can move, how strongly gravity can act, and how finely energy can be divided. Planck energy is a scale born from constraints, not from components. A helpful way to picture this is to imagine a ruler that is not marked by human units, but by the properties of the material it is made from, the stiffness of the ruler, the way sound travels through it, and the smallest notch it can hold all combine to define its markings. In the same way, Planck energy arises from the stiffness of space-time, the speed at which influence propagates, and the smallest quantum of action allowed. Because of this, Planck energy does not answer the question of what something is made of. It answers a different question entirely. It tells us how concentrated energy can become before the familiar separation between gravity and quantum behavior stops making sense. It is a boundary scale, defined not by substance but by the architecture of the universe itself. At this point, it becomes tempting to imagine Planck energy as something tangible, as if it were a tiny object or an exotic particle waiting to be discovered. But quantum physics resists that picture. Energy, even in its quantized form, is not a thing that exists on its own. It is a property of physical systems, a way of describing how much capacity they have to cause change, motion, or interaction. When physicists speak about Planck energy, they are not pointing to a new ingredient of the universe. They are pointing to a scale at which descriptions break. No experiment has ever isolated a chunk of Planck energy, the way one might isolate an electron or a photon. There is no container that holds it, no particle that carries it by itself. It cannot sit still, because energy only appears through processes. A useful way to sense this is to think of temperature. Temperature is not made of particles. It is a measure of how energetic the motion of particles is. In the same way, Planck energy is not a substance, but a measure of how extreme an energetic process would have to be before space-time itself becomes unstable under our current theories. It describes intensity, not composition. This is why the question of what Planck energy is made of feels slippery. It is like asking what a horizon is made of. A horizon is not an object you can touch. It is a boundary defined by geometry and motion. Planck energy plays a similar role in physics. It marks the edge where energy density becomes so great that the distinction between particles, fields, and space-time can no longer be cleanly drawn. Understanding this removes a common misunderstanding. Planck energy is not a building block from which reality is assembled. It is a warning sign embedded in the equations, telling us that beyond this scale, the familiar language of particles and forces is no longer sufficient. Once Planck energy is understood as a scale rather than a substance, another quiet connection begins to appear. Energy and mass, which once seemed like separate concepts, are deeply linked. According to relativity, mass is simply a concentrated form of energy. This means that any energy scale can be translated into an equivalent mass, not because the energy turns into matter, but because they are two expressions of the same physical quantity. When physicists perform this translation for Planck energy, they arrive at what is called the Planck mass. Despite its name, this mass is not associated with any known particle. It is far larger than the masses of elementary particles, yet far smaller than everyday objects. It occupies an unusual middle ground that does not correspond to anything we have ever observed directly. This relationship reveals something important. Planck energy is extraordinarily large when measured on particle scales, but when expressed as mass, it is still modest by human standards. A grain of sand contains vastly more mass. The strangeness comes not from size alone, but from density. If Planck energy were confined to a region as small as quantum physics allows, the energy density would become extreme beyond anything our current theories can safely describe. This is where gravity quietly enters the picture. Mass curves space-time, and energy does the same. At the Planck scale, the energy equivalent of the Planck mass would curve space-time so strongly that the geometry itself would fluctuate. Space would no longer behave as a smooth stage on which particles move. It would become an active participant in the physics unfolding within it. The link between Planck energy and Planck mass shows that this scale is not about discovering a heavy particle hiding somewhere in the universe. It is about recognizing the point where energy becomes so concentrated that gravity can no longer be ignored, even in the quantum realm. This realization pushes physics toward a deeper question, not about what energy is made of, but about how mass, energy, and space-time merge when pushed to their limits. Once mass and energy are understood as interchangeable, the meaning of Planck energy deepens further. Einstein's insight was not simply that mass can turn into energy, but that they are the same physical quantity seen from different angles. Mass is energy that has settled into a stable form. Energy is mass in motion, interaction, or transformation. The distinction is practical, not fundamental. At everyday scales, this equivalence hides quietly in the background. A moving object weighs almost exactly the same as a resting one. The difference exists, but it is far too small to notice. At extreme energies, however, this quiet relationship becomes impossible to ignore. When energy is concentrated enough, it behaves gravitationally. It weighs something. It bends space. Planck energy sits precisely at the scale where this equivalence stops being a detail and becomes the central feature. An amount of energy this large, confined to a quantum-sized region, would not merely participate in space-time, it would reshape it. The curvature produced would be so strong that space-time could no longer be treated as a passive backdrop. The geometry would respond dynamically to quantum fluctuations themselves. This changes what the question of composition even means. If Planck energy were treated as something made of smaller parts, those parts would still carry energy, and therefore gravity. But gravity at this scale feeds back into the structure of space and time so intensely that the notion of smaller parts becomes unstable. The stage and the actors begin to merge. A useful way to sense this is to imagine pressing your hand onto a stretched fabric. A gentle press makes a small dip that does not affect your hand much at all. But if the fabric were infinitely elastic and your hand infinitely heavy, the dip would deepen until the fabric wrapped around your hand itself. At Planck energy, energy and spacetime press into each other so strongly that neither remains independent. Einstein's equivalence tells us that Planck energy is not merely large energy. It is energy that must be taken seriously as a source of gravity. This is the point where the familiar separation between quantum behavior and spacetime geometry dissolves, not because we choose to merge them, but because nature leaves us no other option. As energy approaches the Planck scale, spacetime itself begins to lose the calm stability we usually attribute to it. In everyday physics, space and time form a smooth arena where events unfold in an orderly way. Distances can be measured, durations can be compared, and positions can be defined without ambiguity. Quantum physics adds uncertainty to particles and fields, but spacetime itself remains steady beneath the motion. Near the Planck energy scale, that assumption quietly fails. Quantum fluctuations become so energetic that they begin to disturb spacetime directly. Space is no longer a fixed grid. Time is no longer a uniform flow. Instead, they begin to fluctuate, jitter, and blur in response to the energy concentrated within them. The very concepts of before and after, here and there, lose their sharpness. One way to sense this is to imagine spacetime as the surface of a frozen lake. At low energies, it behaves like solid ice. Objects move across it without deforming it noticeably. As energy increases, cracks and vibrations begin to appear. Near the Planck scale, the ice no longer holds. The surface itself becomes restless, rippling and shifting under the stress placed upon it. Quantum behavior also changes character at this boundary. Normally, quantum effects occur within spacetime. Particles fluctuate, fields interact, probabilities spread out. But at Planck energies, spacetime becomes part of the quantum system. Fluctuations no longer happen on spacetime, they happen to spacetime. Geometry becomes uncertain, not as a measurement problem, but as a physical condition. This is why Planck energy is so difficult to interpret in ordinary terms. The tools we use to describe energy rely on spacetime being well defined. When spacetime itself begins to fluctuate, those tools lose their footing. Energy can no longer be cleanly localized, measured, or tracked in the familiar way. At this scale, the universe does not offer smaller pieces or hidden components. Instead, it offers instability in the very framework we use to describe physical reality. Planck energy marks the point where spacetime and quantum behavior become inseparable, not because of mystery, but because of unavoidable physical consequences. Quantum field theory is one of the most successful frameworks ever built in physics. It treats particles not as tiny solid objects, but as excitations of underlying fields that fill all of space. Electrons are ripples in the electron field. Photons are ripples in the electromagnetic field. These fields interact locally, exchange energy, and evolve according to precise mathematical rules. At accessible energies, this picture works with astonishing accuracy. A crucial assumption quietly supports this success. Quantum field theory assumes that space-time is smooth and continuous down to arbitrarily small scales. Fields are defined at every point. Interactions occur at specific locations. Distances can be made smaller without limit. This assumption is rarely questioned because it holds so well in every experiment we can perform. As energies increase, however, calculations in quantum field theory begin to behave strangely. When physicists push the equations toward extremely small distances or extremely high energies, certain quantities grow without bound. Infinite values appear where finite answers are required. These infinities can often be handled through careful mathematical procedures that reorganize the equations and extract meaningful predictions. This process works because space-time itself is assumed to remain stable throughout. Near the Planck energy scale, that stability can no longer be taken for granted. Quantum field theory allows energy to be concentrated into extremely small regions of space. But as energy becomes more concentrated, gravity responds. The energy itself curves space-time, changing the geometry on which the fields are defined. The background is no longer fixed. The coordinates used to describe interactions lose their physical meaning. This creates a circular problem. Quantum field theory needs space-time to define fields and interactions. Gravity, through energy, changes space-time. At low energies, this feedback is negligible and can be ignored. At Planck energy, it dominates. The theory begins to refer to structures that it simultaneously destroys. The mathematical language collapses under its own assumptions. One way to sense this is to imagine trying to draw precise patterns on a surface that is violently shaking. The finer the detail you attempt to draw, the more the surface moves beneath your pen. Eventually, the act of drawing becomes inseparable from the motion of the surface itself. Quantum field theory tries to draw ever finer details of energy and interaction, but near the Planck scale, space-time refuses to stay still long enough to support the picture. This breakdown does not mean quantum field theory is wrong. It means it is incomplete. Its rules were never designed to operate when space-time itself becomes a quantum participant. The theory assumes a stage that can support actors indefinitely. Planck energy marks the point where the stage begins to respond dynamically to the performance. Importantly, nothing physically explodes or tears apart at this scale in any observed system. The breakdown is theoretical, not catastrophic. It tells physicists that their tools are being used outside the conditions under which they were built. Just as Newton's laws do not fail but become insufficient near the speed of light, quantum field theory does not fail but signals the need for a deeper framework. This is why asking what Planck energy is made of leads to silence rather than substance. At this scale, the idea of composition depends on a background that no longer exists independently. Fields require space-time. Space-time reacts to energy. When both must be treated together, the language of parts and constituents loses its meaning. Planck energy therefore reveals itself not as a physical ingredient, but as a diagnostic. It tells us exactly where our most successful theories stop being self-consistent. It marks the point where energy, fields, and geometry are forced into a single conversation that current physics does not yet fully know how to conduct. As quantum field theory reaches its limits, gravity stops being a distant background effect and steps fully into the foreground. For most of physics, gravity is astonishingly weak. Between elementary particles, it is so small that it can be ignored entirely. Electromagnetic forces dominate atoms. Nuclear forces bind nuclei. Gravity only becomes noticeable when enormous amounts of mass or energy are involved, such as planets, stars, and galaxies. This separation has allowed physics to develop in layers. Quantum theory governs the small. General relativity governs the large. Each works so well in its own domain that for decades there was little urgency to merge them. But Planck energy sits precisely at the scale where this separation collapses. At this energy density, gravity is no longer weak. It is unavoidable. The reason is simple and relentless. Energy gravitates. No matter what form energy takes, motion, radiation, or field excitation, it curves space-time. When energy is spread out, this curvature is gentle. When energy is concentrated, the curvature becomes sharp. At Planck energy, concentrated into the smallest region quantum physics allows, the curvature becomes extreme. At that point, gravity is not something that acts on quantum systems from the outside. It becomes part of the quantum system itself. Space-time geometry responds to quantum fluctuations, and those fluctuations respond to the changing geometry. Cause and effect begin to loop back on themselves in ways that neither quantum theory nor relativity was designed to handle alone. A helpful way to picture this is to imagine writing on a sheet of paper while also trying to fold the paper at the same time. Writing assumes a flat surface. Folding changes the surface. At low energies, the folding is so gentle that writing remains easy. At Planck energies, the folding becomes violent and unavoidable. The act of writing and the shape of the paper can no longer be separated. This inseparability means that gravity cannot be added to quantum physics as just another force. Forces act within space-time. Gravity defines space-time. At the Planck scale, trying to quantize gravity using the same methods as other forces leads to contradictions and infinities that cannot be resolved by existing techniques. The very idea of force exchange presumes a stable notion of distance and duration, which no longer holds. This is why Planck energy is not associated with a graviton detection or a gravity particle waiting to be found at high energies. Even if gravity has a quantum description, it will not resemble the other forces in a straightforward way. It must account for the fact that space-time itself is dynamical and responsive to quantum uncertainty. What emerges instead is a profound shift in perspective. Rather than asking what gravity is made of, physicists are forced to ask what space-time itself is. Is it fundamental, or does it emerge from something deeper? Is it continuous, or does it have a quantum structure? At Planck energy, these questions stop being philosophical and become unavoidable consequences of physical law. The inseparability of gravity and quantum physics at this scale tells us something crucial about Planck energy. It is not a constituent of reality. It is a threshold at which our categories dissolve. Energy can no longer be discussed without geometry. Geometry can no longer be discussed without quantum uncertainty. Each concept loses meaning in isolation. Planck energy therefore marks a kind of conceptual horizon, not a place where physics ends, but a place where it must be reformulated. It tells us that any deeper description of nature must treat energy, space-time, and quantum behavior as aspects of a single structure, rather than as separate ingredients assembled together. This realization prepares the ground for the next step, where physicists cautiously explore new frameworks that attempt to describe what lies beyond this boundary, not by adding new substances, but by rethinking the foundations themselves. When physicists reach this boundary where gravity and quantum physics can no longer be separated, they do not find a finished answer waiting. What they find instead are careful attempts, incomplete but deeply informed, to describe what physics might look like beyond the Planck scale. These attempts are not guesses in the dark. They are guided by the failures of existing theories and by the constraints imposed by everything that is already known to work. One broad effort goes by the name quantum gravity. This is not a single theory, but a family of approaches that all share the same goal: to describe space-time itself using quantum principles. In these ideas, space-time is no longer a smooth continuum. It acquires a microscopic structure, not necessarily made of pieces in space, but of relationships, interactions, or discrete elements that only resemble space and time at large scales. In some approaches, space-time behaves less like a fabric and more like a network. Distances are not fundamental. They emerge from how these underlying elements connect and interact. Energy at the Planck scale, in this view, does not pile up inside a tiny region of space. Instead, it alters the connectivity of the network itself. What changes is not what fills space, but how space is stitched together. This immediately reshapes the question of composition. If space-time is emergent, then Planck energy cannot be made of smaller things located within space. Space itself is part of what is emerging. Energy at this scale becomes a measure of how violently the underlying structure is being excited, not how much material is present. Another prominent attempt is string theory. In this framework, the fundamental objects are not point-like particles, but tiny extended structures called strings. These strings can vibrate in different ways, and those vibrations appear at low energies as the particles and forces we observe. Gravity is not added by hand. It emerges naturally from the vibrations of strings themselves. What matters here is the scale at which stringy behavior becomes unavoidable. That scale is closely related to the Planck scale. When energies are low, strings behave like points, and familiar physics emerges. When energies approach the Planck scale, the extended nature of strings can no longer be ignored. Trying to localize energy too precisely causes the string to stretch rather than concentrate further. This stretching provides a kind of built-in limit. Instead of energy collapsing into an arbitrarily small region, the structure resists. Geometry softens. Interactions spread out. In this picture, Planck energy again does not correspond to a particle or substance. It marks the energy at which the very idea of point-like localization breaks down. What is striking is that very different approaches arrive at a similar conclusion. Whether space-time is treated as a quantum network or as an emergent effect of vibrating strings, Planck energy acts as a threshold beyond which familiar concepts lose sharpness. Energy cannot be confined without altering the framework that defines confinement itself. Importantly, none of these theories claim experimental confirmation. They are constrained by mathematics, consistency, and known physics. But they remain provisional. Physicists speak cautiously here, not because the ideas are vague, but because nature has not yet offered direct evidence. The Planck scale is so far beyond current experimental reach that these theories are tested indirectly through internal coherence and their ability to reproduce known physics in the appropriate limits. This caution is essential. It reminds us that Planck energy is not a mystery substance waiting to be revealed by a better microscope. It is a scale that pushes physics into regimes where even the meaning of observation becomes subtle. Measuring something requires space-time to behave predictably. At the Planck scale, predictability itself is under negotiation. What modern theories suggest, gently and consistently, is that asking what Planck energy is made of may be the wrong kind of question. The deeper question is how energy, geometry, and quantum behavior co-emerge from a more fundamental description that does not privilege any one of them. Planck energy then becomes a signpost, not pointing to a hidden ingredient, but pointing away from the assumption that reality is built from parts arranged in space. In this sense, Planck energy is less like a brick and more like a pressure point. Press hard enough, and the structure you were leaning on changes shape. Physics at this scale is not about discovering smaller pieces, but about discovering which concepts remain meaningful when the old scaffolding is removed. As these theories suggest, cautiously and without finality, Planck energy represents the point where nature stops allowing us to separate what happens from where it happens. Energy, space-time, and quantum uncertainty cease to be distinct ideas and begin to merge into a single, still unfinished description of how reality behaves at its most fundamental level. By the time physics reaches Planck energy, the question of composition has quietly transformed. Throughout the history of science, asking what something is made of has usually led to deeper layers. Molecules are made of atoms. Atoms are made of nuclei and electrons. Nuclei are made of protons and neutrons. Those in turn are made of quarks and fields. Each step inward revealed smaller structures arranged within space. Planck energy interrupts this pattern. At this scale, physics no longer points inward towards smaller constituents. It points sideways toward limits. The equations do not suggest hidden particles or finer ingredients. They signal the failure of assumptions that made the search for ingredients possible in the first place. The idea that reality is composed of parts placed inside a pre-existing space-time stops being reliable. Physically, Planck energy represents the point at which energy density becomes inseparable from the structure of space and time. Below this scale, energy can be treated as something that happens within space-time. Above it, or even approaching it, energy reshapes space-time so strongly that the distinction collapses. The container and the contents merge. This is why Planck energy is never encountered as a material object. It is not something the universe is built from. It is something the universe refuses to let us exceed without changing the rules. In that sense, it functions like a boundary condition written into nature itself. A useful way to feel this is to think about sound in air. At low volumes, sound waves travel cleanly. You can increase the energy and still talk about pitch and loudness in familiar ways. But if you keep increasing the energy, eventually the air itself behaves differently. Shock waves form. Compression becomes nonlinear. The language of ordinary sound stops applying. The air has not revealed a smaller sound particle. It has changed how it responds. Planck energy plays a similar role for reality as a whole. It is the scale at which space-time stops behaving as a passive medium and starts responding violently to energy itself. This response is not an added effect. It is gravity asserting itself as geometry, inseparable from the quantum behavior that created the energy in the first place. This is why physicists describe the Planck scale as a boundary rather than a target. It is not something we expect to reach and then pass through with better accelerators. It is a scale that tells us which questions make sense and which ones dissolve. Asking what Planck energy is made of assumes that energy remains a property carried by objects in space. At this boundary, that assumption breaks. What remains meaningful is relational. How does geometry respond to excitation? How does quantum uncertainty express itself when space-time itself fluctuates? How do familiar concepts emerge when energy is far below this limit? These questions flow outward from the Planck scale, not inward. In this way, Planck energy acts like a horizon in knowledge, not because it hides something forbidden, but because it changes perspective. From one side of a horizon, certain paths are available. From the other, the landscape reorganizes. The horizon is not made of anything. It is defined by geometry and motion. Physically then, Planck energy represents the scale at which our best theories agree on one thing. Not on what exists there, but on what cannot remain unchanged. Space-time cannot stay smooth. Quantum fields cannot stay defined on fixed points. Gravity cannot stay weak. Localization cannot stay sharp. That agreement is remarkable. Independent theories, built for different purposes, converge on the same conclusion. Something structural happens here. Something about how reality is allowed to behave reaches a limit. This is why Planck energy is best understood not as a substance but as a statement. It is the universe saying that energy, when pushed far enough, stops being something that fits inside space and becomes something that defines space. It marks the end of reductionism as a reliable guide and the beginning of emergence as a necessity. And so, the original question finds its answer not in components, but in context. According to quantum physics, Planck energy is not made of anything. It is made meaningful by the way energy, space-time, and quantum uncertainty converge. It is a scale where the idea of being made of parts gives way to the idea of being constrained by structure. What Planck energy ultimately represents is the edge of our current understanding, drawn not by ignorance but by consistency. It tells us that reality, at its deepest level, may not be assembled from pieces at all, but from relationships that only appear as pieces when viewed from far enough away. At lower energies, those relationships settle into particles, fields, distances, and durations. At higher energies, they refuse to stay separate. Planck energy is the quiet boundary between those two regimes, not a brick in the foundation, but a seam where the foundation itself changes character. As the idea of Planck energy settles, it does so without fanfare. There is no final object revealed, no hidden particle uncovered, no smallest brick placed gently on the table. Instead, what remains is a sense of where the universe draws its lines. Not lines of prohibition, but lines of transition, where one way of describing reality slowly gives way to another. At energies far below this boundary, the world feels comfortably structured. Space stretches smoothly. Time flows steadily. Particles behave like entities with locations and histories. Energy moves between them in ways we can track and measure. The universe feels assembled, as if it were built from parts arranged within a stable stage. Planck energy reminds us that this feeling is scale-dependent. It is not wrong, but it is local. It works because the energy involved is gentle enough that space-time itself remains quiet. The stage holds firm, allowing the actors to move freely upon it. As energy increases toward this boundary, the universe does not reveal smaller components hiding underneath. Instead, it reveals sensitivity. The structure that once seemed rigid becomes responsive. Space bends, time fluctuates, localization blurs. The stage begins to move with the actors until the distinction no longer holds. This is why the question of what Planck energy is made of resolves into something softer and deeper. According to quantum physics, it is not made of parts, it is made of limits. It is defined by how much energy space-time can accommodate before it must participate fully in the dynamics. It is a measure of when separation stops being possible. There is something quietly reassuring in this. The universe is not infinitely brittle, fracturing into endless layers of smaller things. Nor is it infinitely smooth, allowing unlimited concentration without consequence. Instead, it has a character. It responds. It resists certain questions by transforming the conditions under which those questions make sense. Planck energy tells us that reality is not merely a collection of objects, but a system of relationships that behave differently depending on how intensely they are stressed. At low energies, those relationships appear as particles and fields. At extreme energies, they appear as geometry and uncertainty intertwined. In this light, Planck energy becomes less like an endpoint and more like a quiet guide. It does not tell us what the universe is made of. It tells us how far certain ideas can be carried before they must evolve. It marks the boundary where reduction gives way to emergence, where counting parts gives way to understanding structure. And so, when we ask what Planck energy is made of, the most faithful answer quantum physics offers is a gentle redirection. It is made of the same things all energy is made of: motion, interaction, change. But at this scale, those things are no longer happening inside space-time, they are shaping it. That realization does not close the door on understanding. It opens a different one. Beyond it lies a view of the universe not as a stack of ingredients, but as a coherent whole, whose deepest behavior only becomes visible when we press against its fundamental limits. And in that sense, Planck energy is not something to reach, collect, or break apart. It is something to listen to, a quiet signal embedded in the laws of physics reminding us that the universe is subtle, structured, and responsive, and that sometimes the most profound answers arrive not as objects, but as boundaries that gently reshape the way we ask our questions.